All right, guys. Hopefully everyone turned in the homework. If you haven't turned it in now, just wait till the end. I assume there's questions. I don't want to spend a whole lot of time answering questions. Like some questions, obviously, I'll answer, but I don't want to spend the whole class on it because we have some new material to cover for the homework that's due Monday. So I'm just going to go to the homework real quick. Homework 9 is due Monday, and that'll be your last homework before the midterm. And then the rest of these are going to be after the midterm. Another thing that I wanted to discuss, I decided to push the midterm up to Monday instead of Wednesday of that week. So it will be Monday, March 7th. And the reason for that is basically I had a review on this Wednesday and then another review on this Monday, and I don't think we need to go over that much review. And if we do, I have this March 5th Saturday where I would be willing to meet and review for the midterm. How many people think, since the midterm is Monday, that you would be interested in attending a Saturday review session? Okay, then that's probably something that I'll schedule, and then whoever wants to come can come. So the midterm will be Monday. Your last homework is due a week before that, right? I don't know what that was. Well, hopefully it didn't interrupt the video. It's always something. I don't know where that came from. Anyway, all right. So yeah, midterm's gonna be that Monday, March 7th.
Monday exams are brutal.
It's better to have the weekend, right, to study.
I suppose, yeah. I just like drinking on the weekend.
Oh, well then, don't drink that weekend.
Because you're honest.
Okay, well, I meant to go back to the homework. So, where were we? So let me just real quick. I know a lot of people probably had problems with 2, A and B, various parts, which is understandable. And then I know a lot of people came to my office and asked me about 1C. How many of you guys had problems with 1C? Pretty good number of people. Did anybody have any problems with A, B, or D on 1? Not really, so there's basically just 1C. Alright, so I guess for those of you I've already solved this problem for, I'm sorry, but I'm going to just really quickly show people who didn't come to my office hours how to do it. Was it the Thevin and Norton that was causing problems, or like the initial finding VC that was causing problems for people in general? How many of you guys had problems finding VC, like from the very beginning? All right. And then how many people had trouble with the Thevin and Norton? All right, so it's basically most of you guys had problems finding VC. Let me draw it. All right, 1 milliamp. This is VC. Okay, so the best way to solve for VC, there's 2 ways you could solve for VC really. You could use superposition if you wanted, right? You could get rid of the voltage source and find what VC is without the voltage source, and then you can get rid of the current source and find it without the current source. That's one way that you could do it. But since I think I've gone over superposition enough, I think it's better for me to go over a different method, which is using KCL, okay? So is everyone comfortable, and does everyone remember that KCL is basically if I have a junction like this, I can call this I1, I can call this I2, and then this total current that flows out of that junction is the sum of those currents. Right? Everyone remember that's KCL. Alright, so you can use that to solve this problem for VC. But first, we need to find this this Vx, because we don't know that voltage either. So what I did to solve this problem, and what you should do in the future if you see something like this, is basically I need to find this current, and I know that their sum is equal to 1 milliamp, right? That 1 milliamp is the total current. All right? So if I needed to make an equation for I1, that's equal to this voltage, right? It's equal to the voltage difference across the resistor divided by the resistance. So it would be 6 volts minus Vx divided by 3K, right? Anybody have problems with that? So that's I1. Now I2 is a little trickier. I could say Vc minus Vx over 9K, right? But then I would be putting another variable in there, and I don't want to do that. So instead what I'm going to do, I know that this 5K and this 9K are in series, right? You see that they're in series? So I can instead, and I know that this is 0 volts because that's ground, so I can say 0 volts minus Vx over this series resistance, which is 14K. That's I2. Does everybody see that? Any questions about that? All right. So now I've got an equation for I1 and an equation for I2, both in terms of Vx. So I can solve for Vx because I can say 6 minus Vx over 3K plus 0 minus Vx over 14K is equal to 1 milliamp, right? Where this is my I1 and this is my I2. All right? So I'm going to go through, I don't want to do the algebra, but basically when you get here, you can solve for Vx and you're going to get 2.47 volts. I just remember because I've solved this problem 9 times in the last 2 days. So that's the voltage you'll get for Vx. Well, once you have that voltage, now you can find the current flowing through the 5K, right? This whole current, that whole current, right? Exactly like we said. I said I2 was minus Vx over 14K. So that would be minus 2.47 volts over 14K, which, if I remember correctly, and I do, is 0.17 milliamps. Okay? That's I2, but that's I2 the way I defined it, right? It's negative. And so if I wanted to define it flowing down, it would be 0.17 positive. So that times 5K gives me 0.88 volts, which is Vc. Any questions about that? Yes.
I thought the 9K and the 5K are connected in parallel.
No. So if you have any resistors connected where the same current flows through them and they share one node, right? That's series by definition. All right. Okay, so that's how you find Vc. I assume some people want me to maybe Thevenize and Nortonize the circuit. How many people want me to do that? All right, I'll do that, and then we'll move on. I need another piece of paper so I don't get too sloppy here. Okay. So this is still... continued. So the original circuit, I'll draw real quick. This is my original circuit, right? And then my load is this 5K, right? Sorry. So when I want to find the Thevenin voltage, let's say I want to do that first. The first thing I do is I get rid of that load. I draw the circuit without my load. This is my 9K. This is my 3K. This is 6 volts, and this is 1 milliamp. All right, and what we're looking for is this voltage difference right here. That's my Thevenin voltage, right? Everyone cool with that? All right, So, what you need to notice here in order to solve this is all over the place. What you need to notice here in order to solve this is that no current will flow through that 9K resistor, right? There will be no current flowing through that 9K. And the reason is because there's an open over here. Basically, if the current tried to flow through it, it wouldn't have anywhere to go, so it just won't flow. Okay? So that means that if I were to look at KCL again, I could say with this junction that my current coming in is this current, and my current leaving is 1 milliamp plus this current, right? Well, this is 0. So that means that this current has to be my entire 1 milliamp, right? Cool with that? Now I know that there's 1 milliamp flowing through this 3K, so I know my drop is 3 volts, which makes this voltage 3 volts. And now here's the part. This is the part that I think got a lot of people. There's no current flowing through this 9K. That doesn't mean there's no voltage here. That means there's no voltage drop across the resistor. Okay? Because the voltage drop across a resistor is equal to the current flowing through it times the resistance, right? Well, if my I is 0, then my voltage drop is 0. That means that nothing gets dropped here, so this is 3 volts. Okay? Any questions about that? So that's my V Thevenin. Alright? So I've got that. Now I'll do the R Thevenin. If I want to do my R Thevenin, I know I short my batteries. I open my current sources. And I still don't have my load. And what I'm going to do is I want to send a current in here, and I want to see how much resistance does it have to go through in order to get back to this other node of the load, right? That's what I'm doing. So how much resistance does it have to go through to get back to the other node? Alright, so now I've got V Thevenin, I've got R Thevenin, right? I can make my Thevenin equivalent circuit. I'm not going to draw that. Now, there's two ways we could solve for the Norton current, right? We can either use source transformation, which is just V over R, right? So my Norton current, I could say it's V Thevenin over R Thevenin, which would give me 3 volts over 12K, or 0.25 milliamps, right? That's one way that we could do it, and that's right. That is correct. But we could also solve for it using the other method where we draw a short across the terminals of the load and we measure the current through there. Does anybody want to see me do that? All right, then we're good. So we're good with this problem. Questions? Yeah.
So if you just did that on the homework, that would have been fine.
Yeah, that's fine. I said that last class. You were probably sleeping.
Yeah, well, that's
What's up?
How do you find the resistance Norton? Like, if you don't want to find it through Thevenin.
It's the same thing. It's the exact same process. So this process is the same thing. It's the same. There's no difference.
Okay.
I just always call it R Thevenin because I'm always coming from doing V Thevenin, so it just makes sense, right? But they're the same exact thing. There's no difference in process.
Okay.
Okay. All right. Anything else here? Yeah.
Are we going to get more time if we don't do the Norton diagram?
Yeah. You got to do the diagrams. I'm just not doing them because I don't want to waste time.
Wait, for the homework we'll get marked off if we don't do the diagrams?
Yeah. The instructions specifically said to use the diagrams.
Oh.
So hopefully you
They said
did.
to simulate them, what I remembered instead.
Well, yeah. I mean, if you simulated them, that's enough. But if you didn't simulate them or solve for them, then that kind of defeats the purpose. All right, is that everything with this one? Okay, I don't want to spend if I go into these, I'm going to be spending the whole class on them, so I don't really want to do that. Is there anything in specific, one of these, like superposition or mesh, that got the overwhelming majority of people?
Superposition. Oh, really?
Here, I'm going to take a vote. How many people struggle with the superposition? Okay, that's a lot. How many with the mesh? That's still kind of a lot. All right, well, what I could do is I could go into today's material and then I could come back to this at the end. Or now that this has already been turned in, I could just make a video solving both of these.
The video would
Are
probably
you guys cool with that?
Yeah, because then you can spend more time on the video instead of wasting it in class.
All right, yeah. So I'll do that. I'll go ahead and solve these by hand, and I'll make a video. I think I could probably do it tomorrow or Friday. So look for it this weekend. But you don't need to know any of this technically to do the homework that's coming up. The stuff we're covering today is getting away from mesh. It's getting away from superposition. It's kind of like totally new. So everyone's cool with me making a video, a separate video? Yes.
Would doing source transformation anywhere make it easier, or
No.
that's just so complicated?
No, you wouldn't. There's nowhere here that you could do that. Yeah.
Just as a question, what do you have for mesh analysis? Do you have any like advice for choosing your loops?
I mean, I personally always choose the loops. If there's a current source, I always choose the loop, the current in the same direction as that current source, because then that's one of your equations, right? If I say that this is I1 and I say it's clockwise, I1 is now 1.2 milliamps. There's no equation. You don't even need an equation. Because
Is there no current contributed from the voltage source whatsoever that you have to worry about?
there is. But what mesh analysis does, right, is it says, okay, I have some current that's flowing in this loop and this loop only. But that doesn't mean that that's the current flowing through this 5K, because this 5K is getting contributions from the loop current in this loop and the loop current in this loop, right? So I1 might be 1.2 milliamps, but that's only this branch right here. As soon as I share it with another loop, then, so say this was my I2, then both of those currents flow through the 2K, and you have to consider both of them.
So then there's no loop in mesh analysis in which you would only have just a singular I1 for one of your equations.
The only way that you would have that is if you had a voltage source and two resistors, and they were the way that you get one where there's only one unknown. Is that what you're saying? Is if
No. I'm just wondering, how would you choose your loops for like 2A, for example?
okay, so if you just want to see how I would choose my loops, let me see if I can. Come on, be nice. All right, so I would choose this one to flow like this, simply because that's the same direction that this current source is going.
Right.
I would choose this one to go like this for two reasons. One, because the battery is minus plus this way, so I'm assuming the current's going to flow this way.
Right.
And also because now my currents are summing when they get to this 2K,
Right.
which I like. I don't like minus signs
Yeah.
if I don't need them. And then this one, again, the battery's polarity is this way, so I would probably choose it this way. That's just, I mean, that's how I would choose them. When I solve these, I still got negative currents because I'm not magic. I can't predict exactly what's going to happen.
Right.
But as a general rule, I typically like to have my currents adding when they get to resistors. So also, if you wanted to just follow that, what you could do is you could choose this one to flow this way, so that when you get to this resistor, those two also add, and these two add. So then there's no real general rule. I mean, if you just made all of them clockwise, it's still going to work.
All right.
So.
I know, like, some people that took Dr. Baker, they were taught to, like, put all their loops in the same direction.
Yeah, it's just not. I mean,
Matter.
he probably wants you to do that just, if I had to guess, it's just because it's simpler in his own head. He doesn't really care about the minus signs and the plus signs. He just is like, well, let me just draw all my loops. It doesn't matter. So I've said to you guys 100 times it doesn't matter. But I still define them how I like to define them. It seriously doesn't matter. Like, whatever you want to do.
I was mostly wondering if you would ever consider doing the big loop.
Oh, you mean like a super mesh?
Well, I mean, like, you could have like the two bottom smaller loops and then use like the overall, like the big outside loop for like a third equation or something like that.
You could do that.
Do you just prefer to do the three inner loops?
Yeah, I was never taught how to do super mesh.
Oh.
That's called super mesh. What you're saying is like use the big loop as a loop. I've never learned how to do that, so I wouldn't even know where to begin. So if it works for you, I mean that's fine. I've just never done that, so I don't teach it that way.
All right.
All right. Okay, so we're going into new material, right? Is that what I said?
Yeah.
All right. All right. Cool. So we're going to talk about power first. Power.
One stupid question.
Yeah.
What is it with electrical engineers, the word super? Why is it superposition, super mesh, superconductor?
I don't know. Well, super. Those are all very different things. I don't know.
It's like turbo, it just makes things sound better.
Yeah, I didn't invent any of that stuff, so I have no way of knowing.
The kind of stuff electrical engineers have nightmares about.
Yes.
All right, guys, power. All right, so this is kind of related to Ohm's law in the sense that you can use Ohm's law to solve for power also. Power is basically a measure of how much energy is being dissipated per second over any number of components. So, for example, let's say I have a resistor. This resistor has, I don't know, let's say that this is, just for the sake of simplicity, this is ground, so this is 0 volts, and let's say this is 2 volts. So, what's the voltage drop across this resistor? Okay. And let's say that it's 1K, which means I have how much current flowing through it? So I know all these things about this resistor. I can find the power dissipated by this resistor by multiplying the voltage across it times the current through it. So instantaneous power, I'm writing instantaneous power because that's important, right? We're going to only talk about instantaneous power in this part of the class. We might get into some other types of power later. Instantaneous power is basically saying this is how much power it's dissipating right now. Other types of power, you know, it can change because you have sine waves and it's always changing. It can be a function of time. When it's DC circuits, the power is instantaneous. Right now, at this moment in time, it is dissipating X amount of joules per second. Right? Everyone knows joules is the unit for energy. Well, watts is the unit for power. Everyone's heard of watts, right? Kilowatts, megawatts. So joules per second is equal to watts. Okay? This is a lot. I'm going to write all these things down. But what I just said is power. The power dissipated by this resistor is equal to the voltage across it times the current through it. V times I. It's that simple. So I would say 2 volts, right, times 2 milliamps, and that gives me 4 milliwatts. That's how much power is dissipated by that resistor. Okay? All right. So V times I is one way to, here, let me write the Ohm's law equations over here again because they're going to be useful. V equals IR, I equals V over R, and R equals V over I.
Have you ever seen V represented with an E instead?
Yeah.
That's, yeah.
Yeah, E is electro.
I asked you about at the beginning of the semester was that.
Oh, that whole wheel, right?
Yeah, we learned it with E, so it's like pi and air is these two formulas, how we remember them.
Yeah, however you remember them is totally fine with me.
I was like, this is really familiar.
There's an app, guys, there's an app called EE220. You might want to download it, it's free. There's a pro version that's like $9. It's really useful. It has the Ohm's law wheel on it. It has resistor color codes. It has capacitor codes. It has data sheets for parts. It's really useful and it's free. And then if you want the paid version, I think it's like $8 or something, one-time fee. It's really, really useful. I've used it all throughout my time in undergrad and grad school. So if you find that on the App Store, I would recommend downloading it. Okay, the reason I'm writing Ohm's law over here is because I just said power is equal to voltage times current, right? But what if we don't know the current, or we don't know the voltage, right? What we can do is we can replace this I. So I just said power is equal to V times I, but I also know that I is equal to V over R, right? Okay. So I could rewrite this as V times V over R, right? And that's another equation for power. V squared over R. And then if I didn't know the voltage, but I only knew the resistance and the current, I could say instead of using V here, I could use IR. And that's going to say power is equal to IR times I, which is I squared R. So right there, that's 3 different equations that all use Ohm's law to determine the power dissipated by a resistor. And now different components dissipate different power. This is just for resistors, and that's all we've seen so far, so it doesn't really matter. Voltage sources and current sources don't dissipate power, they supply power, right? So if I had a circuit, right, like this that I have right here, and I connected a 2-volt battery, and that's basically my entire circuit, right? Well, I would say that the resistor is dissipating 4 milliwatts, and the battery is sourcing 4 milliwatts, right? The battery's not dissipating that power. That power is being provided to the resistor by the power source, right? Okay. So basically, those are my 3 equations for power. Let me write them over here again. Okay. So I think on the next homework I asked, yeah.
So question, if, let's say you were like charging the battery with like a source. So you're charging the battery with a battery. Would it then be pulling that source? Would it then be like dissipating that power over it? Or would that be something else entirely?
So I think you wouldn't charge a battery necessarily with a battery. You would charge it with like a charger.
Yeah.
And so just for an overview of what that might look like, let's say I've got my wall, right? I've got my little plugs, and out of this wall I plug into some box, right? And that's going to charge my battery. So I'll just draw like a 9-volt battery right here, and let's say it's rechargeable. So what I would have is this, there's 120 volts AC coming out of the wall or whatever. This thing would regulate it down to like, say, I guess it would be 9 volts in this case, whatever your battery voltage is. And then charge would pour out of the wall into your battery. And that's how the battery would recharge. So power is not being dissipated in the battery. It's being like, you're pouring electrical charge, which is like electrical energy, into the battery. But you do have power being dissipated inside the regulator, because there's a whole bunch of resistors and things in there burning up power, converting that down to 9 volts. And then in these wires, there might be a little bit of resistance, right? Say I have this wire here and I like blow it up. And I say, I don't know, let's say 2 amps of current are flowing through the wire and it has like 0.2 ohms of resistance. There's power being dissipated there, right? So the more power that's being dissipated, really, you'll start to feel heat because that power is being dissipated as heat. More or less, when resistors dissipate power, they heat up. And so the more power that they dissipate, the hotter they get. And that's the same with most components, but not all components are resistors, and then you have other ways of examining how the power is dissipated by those components. So ideally, like we haven't talked about capacitors and inductors yet, right? But capacitors and inductors don't dissipate power, ideally. They store energy, but they don't dissipate energy. Okay? And you kind of hear me using energy and power interchangeably. That's because the only difference between energy and power is time, right? Their power is telling me how much energy is being dissipated per unit time. Okay?
I have a question then.
Yeah, what's up?
If the difference between power and energy is time, then why do we measure instantaneous power in watts instead of joules?
That's something I've always wondered too.
Oh, okay.
I'm not sure. I don't know.
How many times have we used them?
You guys stump me a lot. Guys, I'm just a student. I'm still a student.
I just work here, man.
My job was to teach you IV. Now you got it. Okay, so I think on some of these homeworks, like I said, homework 9 is the last one before the midterm. real quick, something like this, right? It says determine the total instantaneous power dissipation in each of the following circuits. Okay, so what does that mean? That sounds kind of crazy. You basically solve this circuit, get the voltage here, find the currents flowing through the resistors, and then you solve for the power dissipated by R1, R2, and R3. And then you add them. That's the total instantaneous power being dissipated by that circuit. Any questions about that? So determine the total instantaneous power dissipation in each of the following circuits. Okay, so we just went over the power dissipated by a resistor, right? The only things in these circuits dissipating power are the resistors. The power supply is supplying that power, okay? Whether it's the voltage source or the current source, that's the supply, okay? So if I go here and I want to solve, let's say I combine this 12K and this 8K in parallel the same way we have before, and I find VOA, okay? So VOA is the voltage across R2, it's the voltage across R3. Now you need to find the current through both of them, and then once you have the voltage across it and the current through it, you can find the power dissipated by that resistor. You add those three powers, that's the total instantaneous power dissipation.
Across all three of these.
Right, the total. And then I also ask you to determine the percentage of the total power dissipated by each resistor. So let's say this one, just for the sake of example, this one, dissipates 1 watt, and these two dissipate 2 watts each. Then this one dissipates 20% of the total power, right? 1 out of 5, right? So, does anybody want to see an example? Or, yeah?
Can LT Spice calculate power for us?
LT Spice can do power, but it won't do it in the .op simulations. You need to do transient. And when you do the transient, here, I'll solve one example, and then we'll go put it in Spice, and I'll show you. What time is it? You know what? I'm going to have to go quick. I'll just do a simple example. And then I'm not going to be able to put it in Spice until the end because I don't want to run out of time to get to the other stuff. But I'll show you how to do it. If you want to come see me after. All right, so here's my example. So I got a voltage source, and I've got just a simple voltage divider. Call this 2K, 3K, 5 volts, right? And I want to solve for the power dissipated by each of the resistors, the total power dissipation, and then the percentage dissipated by each resistor. Right off the bat, I know this is a voltage divider, so I can find this voltage, right? This voltage is 5 volts times 2K over 5K, which is 2 volts, right? So I've got 2 volts across this resistor. That means I've got 3 volts across that resistor, okay? Now I want to solve for the power dissipated by these resistors. What's my current here? It's going to be 3 volts, right? V over R. That's 1 milliamp. And the same thing here, right? 2 volts over 2K also gives me 1 milliamp. Okay? So the power dissipated by the 2K is the voltage, right, times the current. That's 2 milliwatts. The power dissipated by the 3K is 3 volts times 1 milliamp. That's 3 milliwatts. All right? So then my total is 5 milliwatts. Right? That's watts, just so everyone knows. All right? So my total is 5. Okay, so what percentage of power does the 2K dissipate? 2 milliwatts out of 5 times, I guess in this case you do 100. So that would be 40%, right? And then the other one is 3 over 5, which would be 60. right? Is that clear? It's exactly the same thing that you're going to do on these problems. Good?
Would you have been okay if we just decided to find I and then do I squared R?
I'm fine with however you want to find it.
Cool.
So our answer to those questions is just going to be the power dissipated by each resistor, and then we add them together.
So the total instantaneous power dissipation, right? That's the sum of all the power dissipated, and then the percentage is just what percentage of the total is each resistor dissipating,
Okay.
right? And that'll help you for the midterm because I put a problem like this on the midterm.
Well, we
Oh.
don't have to find the voltages that are labeled in the questions.
No,
Okay.
I mean no, you don't have to.
So, like, sorry, just trying to wrap my head around the physical world. So, like, let's say your computer takes in so many watts, that would be the dissipation that's the dissipation of it through the entire system.
Mm-hmm.
Yeah, so that makes so much sense.
Yeah, and different components dissipate power differently. And like I said, capacitors and inductors don't dissipate power ideally, but they have internal resistances, right? Nothing is zero resistance. I talked about I talked with someone about this in office hours the other day, how resistance and conductance are inverses of each other. So if something's more resistive, it's less conductive. If it's more conductive, it's less resistive, right? So ideally, we treat these wires as like superconductors. They have no resistance, but they do have resistance. So some power is being dissipated in the wires. Well, that's the same thing with inductors and capacitors. They ideally don't have any resistance, but they do. Parts of them have resistance, and those parts dissipate power. So when you measure the power being dissipated by your whole system, you're basically getting all of the currents through all of the resistances in your entire system. Okay? All right, everybody good with this?
Oh, does that mean kilowatt hours is energy over time?
Yeah.
Oh.
Yeah, well, kilowatt hours is like,
Over time squared, yeah.
yeah, kilowatt hours. Well, a lot of batteries also, you'll see they're rated in milliamp hours or amp hours, and that's basically telling you how long the battery will last if you're pulling this much current from it. All right, so if you have a battery that's like 1,000 milliamp hours, that means it could run at 1,000 milliamps for 1 hour, or 500 milliamps for 2 hours, or 200 milliamps for 5 hours. So that's something that, when we design systems, we take that into consideration. How long do we want the system to last? If we want it to last 20 hours, then we need to make sure that battery's milliamp hours rating, will meet 20 hours. So we have to design our system to only pull this much current, right? All right, so the next thing I want to talk about, and this is the bulk of the homework. It looks crazy. It's not crazy, I promise. It looks crazy. These are called dependent sources, okay? So that's the next thing I'm going to talk about for the next roughly 22 minutes. Also, none of this will be on the quiz today. The quiz is on Seven and Norton. So hopefully you all did the homework. All right, so these are called dependent sources. Okay? Dependent sources, there's 4 types. And it's pretty self-explanatory after I, reveal it. There's current-controlled current sources. There's current-controlled voltage sources. There's voltage-controlled current sources. And there's voltage-controlled voltage sources. And so what do I mean by voltage-controlled, current-controlled, blah, blah, blah? So I'll just start with an example. Let's say I have a little voltage divider. This is just a normal voltage divider. I'll say this is 3K, this is 2K, this is 5 volts. I think it goes without saying that this voltage is 3 volts. It would be 5 times 3 over 5, which would just give me 3 volts, right? Well, now, let's say I connect this circuit to a voltage-controlled voltage source. This source is taking in the difference in voltage between the two inputs. So there's two inputs. There's a plus input and a minus input. And then it acts exactly like a voltage source, but it has some gain. Okay? There's a gain value. So let's say I set the gain here as 2. It's going to take that 3 volts in and it's going to multiply it by 2. And now this is a 6 volt source. Okay? That is a voltage dependent voltage source. So if I were to put a resistor out here of 1K, I connect that to ground. Now I've got 3 volts here, right? I've got 0 volts here, so my input is 3 volts difference. It's taking that difference in, and it multiplies it by 2, so this is a 6 volt source, and this voltage up here will be 6 volts. Okay? And so then I might ask you to find the current flowing through the 1K, it would be 6 milliamps. Alright? Let me go over to Spice and do something like this real quick just so you can see what I'm talking about.
What happens if your voltage-dependent voltage source isn't connected directly to ground? Does it
That-
have to be connected directly?
It does not have to be. That's a really good question. So let's say I'll do the example in Spice and I won't connect it to ground. How about that? So I said, right, I'm going to start with a simple voltage divider. Whoops. Yeah. This is 5. This is 2K. And this is 3K. Alright. And now, when I go into my sources, I think it's E. You see E? That's a voltage dependent voltage source. So that's what I want. And this value E is just telling me the gain. It's telling me what I'm taking in this difference. What am I going to multiply it by? Okay. So this will be the exact circuit that I just set up, and then I'll show you one where it's not connected to ground. So let me go ahead and do this. This is 1K, and then I said I want to find what's the current flowing through that 1K. It would be 6 milliamps is what I said, right? So let's see what Spice gets. I through R3, 6 milliamps. You see the V node 003 is 6 volts. That's this node right here, right? So I took this 3 volts into this source, multiplied it by 2, and I get 6 volts. Any questions there? Yes.
Could you explain the middle part, please?
This?
Here.
Okay, so let me draw a box. So what's happening here is I'm taking in 3 volts
Yeah.
and I'm taking in 0 volts. That difference is 3 volts. This is telling me how much I'm going to multiply that difference by. Okay? 2 times 3. And then that is the rating of this battery now. It's dependent upon whatever this voltage was. Right? Does that make sense?
Yeah.
So then this is now a 6 volt battery. So it puts 6 volts up here. Okay? That makes sense?
There you go.
Alright, so was your question, what if I don't have ground here? Or what if I don't have ground here?
The first one.
The first one. Okay, so just like any other circuit, if I did this, I'm kind of screwed because I don't know this voltage. This voltage is unknown. So I know now that this is 6 volts greater than this, the same way that we would if we had a regular battery.
Yeah.
But I don't know this voltage or this voltage, so it doesn't really help me. So we're always going to connect it to ground. And you could connect it like that. You could also connect it like this if you wanted to. That's basically the same thing.
And if you don't connect the other side to ground, it just changes the difference going into, and then you're just multiplying a different value.
Exactly. So say instead of this, I put my source up here. And I took the difference. That would take the drop, instead of taking the drop across to 3K, that would take the drop across to 2K. So this is going to, let me draw this out. So this is the same thing, except now instead of, and then I would need to ground this, right? Exactly like we were just saying. Okay, so let me run this circuit. Oh, I don't have a .op. So I'll run this. Oh, I didn't set the gain, sorry. So let's set the gain to 2 again and run it. And now this time my voltage here is 4, right? Why is that? That's because I took the drop across the 2K, and this is 5, this is 3, right? So that difference, 5 volts and 3 volts, is what goes into this, and the difference is 2 volts.
2 volts.
So
times
it,
2.
2 times 2 gives me 4, right? Everybody clear? Is that clear? Can somebody shut that door, please? All right. Any questions?
What does this look like in person? Is it like a battery looking thing?
No, this wouldn't. So this would be like an amplifier, basically. We have amplifiers. They're made up of all kinds of transistors and things. And so you have 4 types of amplifiers, basically. You have amplifiers that take in a current and output a voltage. You have amplifiers that take in a voltage and output a voltage. And then, basically the 4 things I wrote down, right? These are all types of amplifiers. So it's a big analog circuit, basically. It has all kinds of components working together to get this gain. And it'll take in a current from somewhere in the circuit, and it'll multiply it by that gain that you set. This is just meant to model those amplifiers. Okay? Yeah.
Does the amplifier also have to be hooked up to some kind of energy source? Because I'm not sure, I
Yeah.
guess, how else it would, okay.
It would, yeah. So this is meant to model an amplifier, but like in real life, let's say I had so we're going to talk about op amps after the midterm. They're called op amps. It's an operational amplifier. Okay, and these are a type of circuit. They basically, it looks like this. It takes in some difference in voltage, and it outputs a new voltage based on the gain. There will be some gain for that op amp. Okay, but this op amp needs to be powered, and it needs to be connected to ground. Otherwise, it won't work, right? Because inside here is a bunch of circuitry, so it's being powered externally. But in Spice, a good way to mimic an amplifier is using a voltage-controlled voltage source or a voltage-controlled current source, and etc.
So it needs its own power source in order to be able to multiply whatever your input source is.
In real life, yes. In real life. And also, so something else that's interesting, and it's not very important right now, but let's say we powered this with 5 volts. That means that this can never be greater than 5 volts. Okay? You can't power something with 5 volts and then get 10 volts out. So this is 0, that's 5. Those are called your rails when you have amplifiers. So let's say we put 200 millivolts in there and 0 millivolts in there, and we had a gain of 10. That would take 200 millivolts difference, and it would multiply it by 10, and I'd get an output of 2 volts. But if I put a gain of 100, that would give me 20 volts. That wouldn't work. It'll output 5 volts. It won't output higher than your rail. So this is all not very important right now. It'll be important after the midterm. But just because you asked.
Do we have time for other esoteric questions, or should we move on?
I would like to, since we have only 12 more minutes, I would like to go into another type of source, because there's the 4 types, right? I think people would probably want to see maybe one of these other types of sources. But just so you see, the 4 questions on your homework, there's a voltage-controlled voltage source. There's a voltage-controlled current source. This is a current-controlled voltage source. And so what's happening here, yeah, what's up? Hold on, just wait 1 second. I got your question, but this is a current-controlled voltage source, right? So I put this 0 volt source here, and there's a current flowing through it. You can't use a a current-controlled source without using a voltage source of 0 volts, because you need this to measure the current through whatever branch you're looking for. So the current that's flowing through here, right? It's going to be 12 volts over 24K. That's going to be 0.5 milliamps. That current will get multiplied by 2K, and now that's going to be my voltage for this battery. It's a current-controlled voltage source. And I need a 2K, like a huge gain, right? Because this current is in milliamps. So I have to multiply by 2,000 to get it to something reasonable for volts. Okay? And that's not unheard of. Like, real amplifiers have gains in the thousands, tens of thousands.
Where do you find that in Spice?
This one?
Yeah.
So this is G, F, and H. So if you just go to Spice and you go F2, E is voltage controlled voltage, F is current dependent current, G is voltage dependent current, and H is current dependent voltage. Okay? So those are the 4 types. I guess I'll do one more example. And then if there's any more questions, since I already did a voltage control, I think it's obvious, right? If I had a voltage drop here, this is 1 milliamp. I'm just going to talk through this, right? 1 milliamp flows through this 2K, so the drop across it would be 2 volts, right? So I would take that 2 volts, and I'm multiplying it by 5 milli. So what would be the current of this source?
2 milli,
It would be 2 times 5,
10 milli.
which would give me 10 milli, right? So that's 10 milliamps, and that would flow in this branch of the circuit. Everybody see that? Yeah. Oh, yeah, you had a question. Like if this was minus and this was plus? So that's also in Spice. If I have E, there's E, but then there's also E2, where these terminals are flipped, right? So it's the same thing. It's just taking in that difference now. So if I were to, let's go back to like my original. Let me take this, put it over here. And then instead of this, I'll put E2 in there, which is the opposite. And it'll just be negative. It's basically like flipping the polarity. And I'll just do a gain of 2 again. Oh, 2. Dot OP. So now instead of 6, it's negative 6, right? Because it's taking 3, but this is negative. So it's taking basically basically taking 3 and flipping it. So it's negative 3 minus 0. Or better yet, it's taking 0 minus 3. It's taking the plus minus the minus. And since the plus is now connected to 0, this is now a negative 6 volt voltage source, right? All right. So I've got about 8 minutes before I want to give you guys the quiz. So let me do one of the current dependent ones for an example. So let's say I had something that looked like this. So this is, you would say VCVS, that's voltage controlled voltage source. Okay, and now over here, let me get another color. I'll do, so I've got a battery, say this is 3K, 3 volts, and then right here I'll put another battery, but that's 0 volts, and I'll call this battery VD, I don't know, something random. And I want to measure the current through that battery, because over here I've got a current dependent voltage source that's dependent on VD and has a gain of, let's say, 2000. Okay? This is 0 volts, right? So what's the current flowing through the 3K? That's right. So I've got 1 milliamp flowing VD, and my source is a voltage source that's 1 milliamp with a gain of 2K. So what is that? 2 volts. So this would give me 2 volts right here. And then whatever this R is, I would find 2 volts over R. That'd be my current, right? Did these seem okay to everybody? They're a little, there's a lot, there's 4 different types of them, but they're all operating on the same principles. One thing I do want to show you is that in Spice, so let's do the current dependent example. So I want to show you guys a current dependent example because I have some notes about current dependent. So let's get a current dependent voltage source. I think it's G. That's a voltage dependent current. Current dependent voltage. Okay. And remember, I need a 0 volt. Oh, not a. See, a 0 volt voltage source right here. 0, and I'll call this VD just because that's what I called it in my example.
And you're just doing that to give Spice something to measure the current through.
Exactly, because inside of this, I'm going to tell it, I want you to reference VD.
Okay.
So value is which source I'm referencing, and value 2 is my gain. Okay? So you need to keep that in mind. It'll be in the video, obviously. But keep in mind that when you make these current dependent ones, value is the source that I'm referencing. It's the source's name, so it's VD, right? And then the gain, what did I say, 2K? And then you want to make it visible just so you can see them both. There's this little visible thing right here. You can make stuff visible and invisible. I would just make it visible so you can see them both. And then maybe you can, grab them and move them if you want. So now, throw something together like this. I don't know. Okay, so what did I have? I had 3 volts and I had 3K. So let me just .op and I'll run it. So we see that I get 3 volts, right? Obviously right here. I drop across this 3 and I get 0 volts because this is a 0 volt source. It's connected to ground. And so my current flowing through this branch now is 1 milliamp. And that 1 milliamp gets multiplied by 2K, so this is a 2 volt source. Okay? Any questions?
Which type is this again?
This is current dependent voltage source. So you would, or you can call it current dependent, you can call it current controlled. I like to say current controlled. So this is a CCVS, current controlled voltage source. Yes.
Is it not, so in Spice we have to declare what current we're looking for, which is in this case we're looking for the current that relates to VD, that's flowing through VD. Is it not kind of obvious what current source we should be looking for? Because even if 2 currents, for instance, were going into this current controlled voltage source, it would just have to take the net of those 2 currents, correct?
I think it seems simple because of how simple I made the circuit over here, right? If I took, let's say I took this circuit and I attached a current controlled voltage source somewhere else, you wouldn't know which of these currents I wanted unless I put that voltage source in there and named it, right? Because there's different currents flowing through all of these loops. So say I wanted it to, and this is the case, right? With real amplifiers, there's going to be nodes all over the place in your circuit, and only one of those is the one that you care about being the input to your amplifier.
Right. Well, I guess the question that I have is, in real life, you're not going to have to specify which current you want it to look at because there can only be one current going to it.
Exactly. Yeah, that current would actually physically be connected to the input of your amplifier, but in Spice, this is just the way that it's simulated.
Gotcha.
Yeah.
So do you actually have to connect the current controlled voltage source to the original circuit in and of itself, or could you just put a ground there and do it like that?
You could do it like that. If you're saying, can I just do this?
Yeah, you can just cut that off and then put that there.
Yeah.
I'm just curious if it had any if it was actually pulling the current from there. Because that was kind of my question, does it not?
It's just the same ground. It's just all ground. It's just one big reference.
So
But
these two circuits are connected.
they're connected to the same ground.
Right.
But
And then so as a result, what was it? The current controlled voltage source is going to interact with the circuit on the left.
no, it won't.
Oh, okay.
It won't. Because this ground is just a big return path for pretty much everything. These circuits are completely independent of each other. They're just connected to the same ground. You can't have different grounds per se in Spice. It's all one ground. You could in a real circuit, but it wouldn't be a good idea.
Well, I guess that's what I'm asking. In a real circuit, would these circuits interact?
their currents would return to the same ground, but they're not going to influence each other.
Okay.
So this is physically the same piece of copper or conductor that they would be connected to, but this voltage source is not going to have any say in what happens to this resistor, because nothing up here is connected. They're just returning to the same return path.
Okay.
Okay, and it's hard. It's hard.
Now,
Ground is
I
kind of
remember
confusing.
talking to you about it previously, but ground is still scary.
Yeah, ground is a little confusing. I just got nervous again, guys. I thought this was 1 minute. It's an hour. I was like, what is it doing? All right. Any questions? I don't think the quiz should take you guys a super long time, but would you prefer to give the quiz now, or does anybody have any questions? One last question.
Could you run it real quick? Is that,
I did run it. Yeah, I just didn't label anything. Here, let me label this stuff for you real quick. Let's call this V in. We'll call this, well, that's ground, right? This is 0, so I'm not going to label that. Whoa, well, why is that 0? What just happened? Okay, it's good, it's good. Yeah, that's 0, right? So, you just wanted to see the .op or what?
yeah.
Is this good?
Well, I thought they weren't supposed to interact with each other.
They're not interacting with each other.
Why is the voltage, the current control voltage source creating a voltage of 2 volts?
Well, I thought you meant. Wait, hold on. Hold on. Obviously, if this is literally dependent on this, that like by definition.
Yeah, sorry, it's software dependent in this case. It's like in real life there would be no wire, so you couldn't just like telekinesis the electricity from one point to another.
In real life, there would be a wire.
Yeah.
What
But-
do these components actually look like?
In real life,
Uh-huh.
they're very complicated analog circuits that consist of many different components. Let's see, just real quick. Let's look up like a op amp schematic. There you go. Let's see, where is it? There you go. This. So that would be what an amplifier would look like, right? There's all kinds of transistors and resistors and capacitors and things inside. So we analyze it as like a box, right? I drew it on the paper, just like this.
Go back to that Wikipedia page for just a second.
Yeah.
Scroll back up to the picture that was at the top of on the Wikipedia page where you found the picture. So all of that in that schematic is packed into that.
Exactly. Yeah, isn't that crazy? Yeah, I talked to some people in my office hours about like nanotechnology, and like what we do in our group is like we design chips, and so you have like hundreds and thousands of transistors on a chip. Maybe if we have extra time on one of the review days, I can kind of like discuss like an overview of that stuff, because it's really interesting, like very interesting stuff, right? That all that crazy stuff could be packed inside something that's small, because that actual size is probably about this big. So you get into like micro like micrometer sized components and things like that. So all right, without any further delay, I'm going to give you guys the quiz. You got about 12 minutes to take it. It shouldn't take you that long.